we left off with line integrals. So last time we talked about line integrals in general, right? We talked about what they were. We did them as a function and we did them over a vector field. And in particular, over a vector field, we were talking about it determines to what extent when we're going through along a path through a vector field that we're going with or against the vector field. That's what the line integral gives us. Now, what does that mean in a context? Well, it depends on what our vector field is. If our vector field is a force field, it gives us the amount of work done by the vector field as we travel along that path. So today and Tuesday, we're going to be very concerned with some other ways of solving line integrals. What we did last time is we had a parameterization for the curve, and that allowed us to change the line integral, the f dot dr, into a single variable integral, and we would calculate. Today, we're going to learn how to do it in a very specific case, and it's going to give way to what's called the fundamental theorem of line integrals, which we can use, but only in certain cases. So we're going to talk about what it is, when we can use it, and when we can't. And I think you're going to like this one today because this is a very quick way to solve a certain subset of line integrals. All right, so particularly we're interested in gradient fields. Remember, just as a recap, we know how to find the gradient of a function. That gradient is a vector made up of the partials, right? That creates a vector field. So all gradient fields are vector fields, but not all vector fields are necessarily gradient fields. So that's just a recap. If what we have is a gradient field, the function that would produce that gradient is called a potential function. All right. So, one of the ones we've done a lot is the function x squared plus y squared has the gradient 2x comma 2y. X squared plus y squared would be the potential function for that gradient field. Now, if we wanted to get the change between 2 points, given that vector field, well, we would just use the potential function and take f at our final point minus f at our initial point, get the net change. The other way we could do it is we could take some path between the 2 points, break it up into a bunch of small pieces, and figure out how we're moving along that path to get the work done, to get the net change. That's the line integral. So basically, these are two different ways of calculating a line integral if what we have is a gradient field. The potential function at P minus the potential function at Q, or the line integral of the gradient field along our path. The latter of those two is what we were doing last time. This is what we're going to do this time. And this is what we call the fundamental theorem of line integrals. And the reason it's called the fundamental theorem is because it's exactly like the fundamental theorem of calculus, right? If you remember the fundamental theorem of calculus, that's how do you solve an integral from A to B. The derivative of capital F is little f. So capital F is an antiderivative of little f. Yeah. Then the integral from A to B, and this is if we're continuous on this interval, is equal to f of B minus f of A. So that's the fundamental theorem that you learned back in Calc 1. Much familiar name, I figured. All right, so that's what we're referring to here, that fundamental theorem. Except we're doing it for line integrals. Now, we're using the ideas from the previous slide, but let's think about this for a second, right? We're doing the f dot dr, but remember that f is the gradient of some potential function, which means it came from the derivative of some potential function. The integral tells us to take the antiderivative, which gets us back to the potential function. And so all we need to do is do the potential function at Q minus the potential function at P. We don't have to go through the parameterization steps. We don't have to go through the dot product. All right. But again, this only works if our vector field is a gradient field. All right, so only in those specific cases. So before we start doing the fundamental theorem, let's dial that down, because we know we have a hypothesis we have to satisfy, right? We have to have a gradient field in order for this to work. Well, how do we determine if a vector field is in fact a gradient field? This is something we actually did talk about last week. So feel free to shout it out if you remember. So f is the potential function for f. So that's the only difference here, is now instead of capital F being the antiderivative of little f, f is the potential function of the vector field, which we found is a gradient field. All right, we won't go through the proof, but just a couple things that some of this we talked about last week. The first part we didn't. First off, if P equals Q, we have what is called a closed path. All right. Closed path meaning we start where we end, right? There's nothing crazy going on here. So we start at point D, we go along C, and we end up back here at Q. That's a closed path. That's what it's saying. All right. Well, if P and Q are equal, this statement will seem really obvious here once I go back. If P and Q are equal, then basically we're looking at f of Q minus f of Q, or f of P minus f of P. So the line integral would be 0. And that's for any closed path, right? Because all we care about is where we start and where we end. Hence the term path independent. Does that sound familiar? So if our vector field is a gradient field, it is path independent, because it only depends on the endpoints. It doesn't depend on the direction. We had another name for path independence last time, conservative. So I'm going to keep saying this because I just want you to take all these terms together. If we have a gradient field, it is path independent. It is a conservative vector field. And those are all bidirectional. If we find we have a conservative vector field, it is path independent, therefore it is a gradient field. These are all guaranteed. Now, what's nice about this is we did this on Thursday, I believe, last week. We figured out how to determine if a vector field was conservative, and we did a couple of them on the worksheet. You remember what we had to do? We had to show the curl was equal to 0. So here's what's cool. We now know that if we have a gradient field, we can use the fundamental theorem of line integrals. Awesome. We also know how to determine whether a vector field is conservative / path independent / a gradient field. All we have to do is show the curl is 0. If the curl is not 0, it's not conservative. We cannot use the fundamental theorem of line integrals. All right. So that's why we were taking the time to do that last week, was because now it's a big tool for us, because if the curl is 0, it is so much easier to use the fundamental theorem of line integrals than it is to have to go through the parameterization, do the dot product, and possibly get a messy integral. So we actually already talked about this. Now this is going to go into a little bit more. Basically, if it's path independent, then it doesn't matter what path I take between Q and C on a closed loop. Those are always going to come out to be 0 if it's path independent. Okay. Well, we can't check every closed path, right? Because there's infinitely many. If any closed path comes out to be non-zero, we already know it's not conservative, therefore it is not a gradient field. Okay, so if you show any closed path is non-zero. Could be a circle. You know, we've done a lot of circles, right? So that's basically what this slide's saying. I don't want to spend a lot of time on it because this is great, but this isn't something we can show. We can't test every possible closed path. It's not possible. Now we can show that it breaks down if we found one non-zero closed path, but that doesn't help us as far as showing that something is a vector field. So let's talk about doing it algebraically. For example, this very basic vector field right here. If you remember, actually, let's talk about the curl test just because I want to bring it back up just to refresh it. We'll talk about the curl test in 2D, and then we'll talk about it later in 3D. So just a reminder, so this is actually a refresher. We're going to go back and talk about the curl again. So if the vector field, let's call it F1, F2. Well, remember, those are the first order partials of the potential function. We know that the mixed partials should come out to be equal, right? That's something we learned a long time ago. So what we need to show is that that curl is 0, or that these mixed partials are equal. It's better to show that the curl is 0 because next week when we talk about Green's theorem, when we have a non-zero curl, that becomes useful for us with Green's theorem. So that's why we always just say, hey, let's just show the curl is 0, as opposed to show that the mixed partials or these second order partials are equal. So this is all we need to show. df dt dx minus df d1 dy is 0. If it's not 0, again, not a gradient field, not path independent, not conservative. Okay, we have to use one of the other methods for solving line integrals. Could have been the one from Tuesday, could be Green's theorem that we're going to learn next week, could be Stokes' theorem that we're going to learn week after that. But it just tells us that the fundamental line theorem doesn't work. We want to use the fundamental theorem. Gradient fields are great, they're path independent, they have a lot of really cool properties, but we can't always, right? It's a specific case. So that's our 2D curl. So let's talk about how we would use this guy to show. Okay, so remember F1, F2. Here's the only thing that you need to have in mind. You don't even have to memorize it, right? Because you can have it on your note cards. Is that you kind of switch, right? It's df2 dx. So it's the second guy with respect to y. So if we're calculating this curl, it's d dy of xy minus d dx of 2xy. We have a lot of practice finding partials. I'm pretty confident that you guys are feeling comfortable with partials at this point in the semester. I've seen it. So d dy, the derivative of this with respect to y is x. d dx, the derivative of this with respect to x is 2y. That does not equal 0. This is not conservative. Right? It doesn't mean it's not solvable. It doesn't mean we can't find a line integral over it. It just means it is not conservative. Therefore, it is not path independent. We would call it path dependent. And we can't use the fundamental theorem of line integrals because it's not a gradient field. Okay. So again, it doesn't mean there's anything wrong with it necessarily. It just means it's not a gradient field. And today we are specifically interested in gradient fields. So this too is going to kind of use that space. Let's do. So this is basically our curl test. Now there is something important, and we're going to look at this here in a second. The domain of F, the domain of our vector field, does have to have the property that every closed curve within it encircles a region that lies entirely in the domain that there are no holes. That I will address here in a second, but I want to show you how this works in practice. So we like it when our curl is 0. We love it because that means we have a gradient field, and if we have a gradient field, we have a potential function. We did this one last time. Anybody happen to write down what the answer was by any chance? It was negative 1.6 something, but we had an exact answer. I can't remember what it was. If you happen to find it, let me know. But let's all right. So here's what we would do. That's okay. We're about to solve it again anyways. All right, so here's what we do in practice. So we've got a vector field of negative y sine x cosine x. First thing we do is we run the curl test. So that means we do the derivative. So this is our f1, this is our f2. So the derivative with respect to x of cosine x minus the derivative with respect to y of negative y sine x. And what do we get? Well, the derivative of cosine x with respect to x is minus sine x, minus the derivative with respect to y of minus y sine x is minus sine x. We get a curl of 0. That tells me this is a gradient field. Now, we did this one last time via parameterization, but this tells me that we can use the fundamental theorem of line integrals, which says that I can do, if we're trying to do f dot dr over some path c, I can actually do f of, let's call them q minus f of p. That was that fundamental theorem. Well, we're given q and p, 0, 0, and 2, 4. What we need now is f. We have to find the potential function. In other words, we have to find the function whose gradient is minus y sine x and cosine x. All right. So that's what we need to do. Well, let's think about what that means. That means when for some function here that kind of sat up above this, taking the derivative f sub x, right? This is f sub x. This is f sub y. So when I took the derivative with respect to x, I got this. When I took the derivative with respect to y, I got that. So how do we do that? Well, I'm going to give you kind of a formal way, but you can also reason through these, right? You can think about, and I know a couple of people did it last time. You can kind of think about, okay, well, I need something that gives this as a derivative and gives this as a derivative. But here's a way you can do it a little more formally. So we're going to do the antiderivative of minus y sine x with respect to x. And we're going to do the antiderivative of cosine of x with respect to y. Remember what that means. X is the variable, y is a constant. So if I'm doing this guy, it's going to be over here. Minus y is a constant times the antiderivative of sine, which is negative cosine of x. And then plus, now here's the only thing that we have to be a little careful about. There does need to be a plus c. There could be a constant. Remember, with the fundamental theorem, we don't care about constants because they would cancel out anyways. But one thing we do have to be aware of, because y would have been a constant with this, there could be some piece of the function with respect to y still, right? So there could be some piece here that only depends on y. Does that make sense? Because when we took the derivative with respect to x, it would be 0. Just like when we take the derivative of a constant is 0, we have to account for the constant when we go backwards. In this case, because I'm only doing an antiderivative with respect to x, I have to account for the fact that there could be a piece with respect to y that just went away. So this is a way of formally doing it. And this is just kind of the notation I use. You'll see some different notations here. You use whatever makes sense to you, but just remind yourself, okay, there could have been a plus a y squared here because it would have been 0 taking the partial with respect to x. Now here, the antiderivative of cosine x with respect to y, because that makes cosine x a constant. So the antiderivative is cosine x times y plus could have been a piece with respect to x. Could have been. So simplifying these, the negative and the negative, we get y cosine x. Again, I'm going to put it here for right now, just because I want you to just be aware of it. Here, y cosine x plus some piece with respect to x. Well, right there and there, they're already equal. So we actually don't need those. There is our potential function. The y cosine of x. So now we'll do it with this guy. So we're going to plug in our points, 2, 4. So let me actually write this. 4, f of 2, 4 minus f of 0, 0. So we're going to have 4 cosine of 2 minus 0 cosine of 0. And there is our exact answer. That's that negative 1.6 whatever that we found last time with Symbolab. And remember, there was something in terms of a cosine. And remember, because the question came up, oh, it's negative because it's cosine of 2. Or a statement, I don't think it was a question. That's the fundamental theorem of line integrals. That is basically our procedure. So just let me recap the steps. And then we'll go on because I want you to see another interesting example. All right, step 1. You're given a gradient field and some path, and you're asked to find the line integral. Okay, first thing you do is the curl test. If the curl comes out to be not 0, as of right now, if you're still trying to solve it, you're doing what we were doing on Tuesday. Next week, we'll have Green's theorem into the mix too. If it comes out to be 0, we now know it's a gradient field, which means we can find a potential function. Again, this is more of a formal way of finding a potential function, but you can reason through it. You find a function whose gradient is this. Once you have that, all you need to do is plug in your starting point, your ending point and your starting point, find the difference, and you are done. There's no parameterization needed or any of the stuff we were doing on Tuesday. We get to skip that. And we get to skip it because it's a gradient field and because it's path independent. The only thing we need is information about where we started and where we ended and the change between those two. Questions about that? Like I said, very powerful, but it does require that we have a gradient field. So that's going to be, I'm going to do probably just one more example. And then cut you loose on the worksheet. And that's what you're going to be doing today. Determining whether or not you have a gradient field. And if you do, you find a potential function. And then once you have the potential function, you run your fundamental theorem of line integrals. All right, that's going to be our focus for today. But I want to show you one thing that we do have to be careful of. So we're going to do one more example. All right. So there's our vector field. All right, so first off, first, like I said, first step, you were given a vector field, run the curl test. Okay? Because if the curl is 0, we might have a gradient field, or we do have a gradient field, I should say. And we can work from that. Okay, so it's going to be d dx of x over x squared plus y squared minus d dy of negative y over x squared plus y squared. Right, so not the prettiest ones that we've ever had to deal with. Quotient rule, or we could set them up as a product. We'll probably let's just use quotient rule. All right. So quotient rule is, leave the denominator alone times the derivative of the numerator with respect to x. Now we leave the numerator alone, so x times the derivative of the denominator. Oops. 2x. That's not an x. I'll get this right sooner or later. All over the denominator squared. Okay. You're not worried about multiplying that out. We're going to have a denominator squared on the other part. So we don't need to make extra work for ourselves. We'll simplify the numerator here in the next step. This one's going to be very similar, right? Now, except now we're doing it with respect to the y. So x squared plus y squared, we leave that alone. Derivative of this guy is -1. Oops, minus. Now a negative y, and then derivative of the denominator is 2y. All over x squared plus y squared squared. All right. Got to simplify those numerators in order to see what is going on. So over here, we got x squared plus y squared minus 2x squared. So we got x squared over x squared plus y squared squared. Minus, now here, I got a negative x squared, because I'm distributing this -1. Negative x squared minus y squared plus 2y squared all over x squared plus y squared squared. Okay, you probably already see what's going to happen, but I'm going to go to the next step just to make it really obvious. And x squared minus 2x squared, that becomes y squared minus x squared over x squared plus y squared squared minus a positive 2y squared and a negative y squared once again gives us a positive y squared. So y squared minus x squared over x squared plus y squared squared. We get 0. We love that. Again, something interesting happens in this one, and there's a very specific reason. Okay, I didn't leave myself a ton of room, but I think I've got enough room to do this. Let's hope this doesn't get. If you can't see it at home, let me know and I can move to a different part of the board. Okay, so we're going to do a calculation the way we would have done it on Tuesday of the f.dr. And C is going to be the unit circle centered at the origin, and we'll just go counterclockwise. So a very easy path. This is one that, like I said, if you're not used to it yet, you will be. That's going to be x equals cosine of t, y equals sine of t, and we're just going to go from 0 to 2 pi. We'll see that one a lot. Okay, so that basically is our r, right? That tells us that our r is cosine t, sine t. So our dr is the derivative of that, negative sine t, cosine t, dt. Now the other thing we'll do is, and I didn't leave myself a whole lot of room to do this, so bear with me on this. Remember what happens next. For x and y, we plug in cosine and sine, right, into our vector field. And our vector field is the one that's on the slide, right? It's negative. So I'm going to plug it in over here just because I do want you to see what happens. So negative sine t over, and look at what's going to happen here, right? Cosine squared t plus sine squared t. And yep, cosine t over cosine squared t plus sine squared t. So it turns out when we plug that in, the denominators are just a Pythagorean identity, right? So they just become 1. So we end up with just negative sine t cosine t. All right, so and putting this into our f.dr over our c, we know we're going from 0 to 2 pi. And we have negative sine t, sorry, this is probably going to be a lot smaller than I would like it to be, cosine t dotted with negative sine t, cosine t, dt. So 0 to 2 pi. We're going to end up with a sine squared t plus cosine squared t dt. Pythagorean identity again. So we end up with 0 to 2 pi of 1 dt, which is just 2 pi. Now, here's the problem. We just did a closed loop, right? We did a circle. We ended where we started. If this were following our theorem, which says that a gradient field is path independent, we should have gotten 0, but we didn't. This is the one thing we have to look out for. And the reason it failed is because of a point that was included in our circle. So we did the unit circle. And let me go back to the theorem that guarantees us this. The domain of F has the property that every closed circle in it encircles a region that lies entirely within the domain. We have a hole, and if we go back to our vector field, we have a hole at the origin, because at 0, 0, this is undefined. And that is enclosed in our circle. And so that's why it doesn't work for this path. It would, now outside of this path, if we did some other closed loops, we would have been okay. But this specific one, anything that's going to go around 0, 0 is going to be a problem, and it's because there's a hole there. Now, you're not going to be getting a whole bunch of vector fields that have a hole in them. I just want to make you aware that this is something that happens if you have a vector field that has a singularity, a point of discontinuity, because that's where things go crazy. Things go to infinity and rules break down. Even the fundamental theorem calculus in Calc 1. If we're not continuous on that interval, we lose the guarantee of that. All right, so this only works when we have a nice continuous vector field. I always like to do this example because it is one that, you know, it makes it very obvious where the issue is. It doesn't happen often, and we're not going to see a whole lot of vector fields with singularities or points of discontinuity. But I want you to be aware of it, that, hey, this is the case where our theorem, it's not included in our theorem, right? Our theorem says this is only guaranteed if you have no holes. Questions about that one? And so again, we still solved it, right? We still calculated the line integral. We just lose the guarantee that it's path independent. Okay. I'm not going to do one of these. There were a couple of them on the worksheet last time. There's 1 or 2 of these on the worksheet this time. But in 3D, the curl test still works. The biggest difference is because it's 3D, we're now getting a 3-dimensional vector instead of just a basically it's not really a scalar because it does have magnitude and direction. Plus tells us which way the curl is turning versus negative, clockwise versus counterclockwise. Whereas in 3D, we have infinitely many directions. Remember, we were talking about the right-hand rule. So if our curl is going this way, our thumb is pointing in the direction of the vector we get from the result of the curl, the axis of rotation. So there's obviously all these infinitely many axes in 3D. But the curl test also still works and everything holds. And one of the things that we talked about in here last time is because it has to be equal to the 0 vector, which means all 3 components have to be 0. If any of these components are not 0, you know, if any of these 3 components are not 0, we're done. You don't have to check all three components. If you already get the first component's not zero, and all you're really doing is the curl test, you're done. You already know it's not conservative and it's not going to be a gradient field. But if you get 0, 0, 0, you know that you have a gradient field, unless of course we have a hole. But as long as we don't have a hole, we have a gradient field, there will be a potential function. And we just need to find that potential function, and then we can use the fundamental theorem.